Okay, so let's move on into how to diagnose and how to implement, from a technical point of view, MCMC. So, just as a quick reminder, we have two ways: Metropolis algorithm and Gibbs sampler, and they are very similar, and also they converge in the infinite, and they just get to the same place, but normally Gibbs sampler is more used. And as you can see here, the results are very similar regarding inference, that there are point estimates and highest density intervals, and also the shapes of the distributions. So now, what we can specify to make an MCMC happen? First of all, we need to specify the sampling method. Normally, it's called Hamiltonian Monte Carlo method. That is a current method, but there are other methods available if this is desired. We also need to specify the number of chains. Normally 3 are enough, but you can increase them if you want to 4 chains or 5 chains, for example. Then you need to specify the number of pure samples that are going to make it into drawing the posterior. But also can happen this type of scenario. As you can see here, there's a stable trend, but at some point in the first values, very weird values are going there because the MCMC is searching for the hot zone, okay? So a solution to this, because all of these values, if they are taken into account, can damage convergence and also make unrealistic values into the inference. It's called the burn-in samples or the training samples, okay? So basically, it will divide and it will cut out all of the first iterations, of the chains, and just remove them, okay? So first of all, it's good for the efficiency of the computing time and space, because they will save space that it will occupy, and also with no need. And also because the estimation of the chains at the posterior will be better, more precise, okay? So you will need to specify how many burn-in samples you will like to have. And for example, if you specify 2,000 pure samples and 500 burn-in samples, the overall samples will be 2,500, okay? There's also another thing to do or specify that is called the thinning of chains. Okay. The thinning of chain is basically ordering the computer to only store in the memory 1 out of k steps. For example, if k is 10, only 1 step out of each 10 will be stored. So as you can see here, when you have an ideal posterior to replicate, this is the raw chain from the starting values to the actual the pure samples, and the thinning will be to select all of these values to make cheaper and less heavy regarding space requirements distribution to make your inference. So thinning is normally a pretty good thing to count. For example, I'm making the thinning for 3 values or to 5 values, depending on the number of samples that you specify. Okay, so how we can interpret an MCMC output? First of all, we need the chains to be realistic regarding the posterior, to be large enough to be stable and precise, and to be efficient in resources, in time and space or power, okay? So first of all, the representativity can be diagnosed with 2 metrics. First of all, the trace plots and a visual inspection of them, and also convergence diagnostic. A trace plot is something like this. It's a plot when you have the raw values that each chain will assign to each iteration. So as you can see here, we have 3 chains: dark blue, black, and light blue. And the form to seek here is basically a caterpillar, something like a caterpillar, okay? That is basically a random variation in all of the chains that, without many differences between them, that can be more or less constricted in a zone. If that is happening, everything is okay. So a problem would be that there were systematic differences between the chains, or that any other form that is not a caterpillar, okay? The other thing to have regarding the representativity of values is convergence diagnostics. Then we have the PSRF statistic, that is called the potential scale reduction factor. This is also called Gelman-Rubin statistic, shrink factor, or R-hat statistic, okay? So this potential scale reduction factor needs to be lower than 1.1. This criterion can be flexible at some times, but normally it's not recommended. And as you can see here, we can see how this metric just it starts to decrease as long as the iterations start, and everything is below 1.1 when the iteration stops. So that's a good thing. Next, we need the values of the change to be precise. So first of all, a very useful concepts here are the autocorrelations, that are the correlations of the values of each step of the chain with the previous ones, okay? So we need them to be descending, approximate to 0 at best, and without differences between the chains. So as we can see here, there are significant differences between the chains, although they are descending. So this is a red flag. And also, one of the chains is not proximate to 0 at all, like it's around the 0.6. However, the other chains are more proximate to 0. Okay, so the ideal thing to find is that there are no differences between chains and all of them are descending and very near 0. The other things to look for are the convergence diagnostics. Effective sample size need to be greater than 10,000, but this is kind of secondary if we are not interested in intervals. And basically, this statistic is the number, the total sampling number divided by the autocorrelation. Okay, and the MCSE, or Monte Carlo standard error, that is basically the standard deviation divided by the square root of the effective sample size. Okay, so this number is basically the estimated standard deviation of each chain. And we can plot all of the density curves of each chain to first of all see if the density curves are okay, if they are given realistic values, if they are very similar between all of the chains, and also we can calculate the MCSE, or the Monte Carlo standard error, because it is expressed in the metric of this parameter. So we can infer or interpret them as if they are given realistic values or not. For example, if we are inferring things for Cohen's d, an acceptable Monte Carlo standard error will be like 0.01 or 0.05. If the Monte Carlo standard error for a Cohen's d is 2, that should be completely unrealistic unless we are dealing with incredibly dispersed and heterogeneous sample of Cohen's d's. Okay, so the last part is for the change to be efficient, because we need computation time and computation power. And for example, having an overnight MCMC estimation going on can be a common situation, but it's better not to do that, because it's wasted time and wasted resources, or something that also can appear to be wrong if we are not getting into the right one. Okay, so there are many ways to help us saving time and saving power. One of them is the parallel execution, that there are many methods in R and other software to make that. Just the sampling method, for example, Hamiltonian Monte Carlo. But there are also other alternatives if we need them. And we also can change the parameterization. For example, use differential scores instead of raw scores in a regression, if that's the case. In addition, we can save computing power with, for example, the so-called thinning of chains. If we select that thinning to be taken place, we can increase thinning to decrease the computational space that is required. Okay, so here's an example of adequate MCMC. As you can see here, the trace plots indicate a caterpillar shape in all of the chains. The autocorrelations report very low differences between each chains and very proximate to 0. The shrink factor is lowering and being stable in very small values and below 1.1. And also the density plots, or the density curves of each of the chains, are very similar between each other. The 95% highest density interval is very similar between chains, and the Monte Carlo standard error is this number that is very low, and probably realistic values regarding this parameter. However, this is an example of a problematic MCMC. There is no caterpillar form here. There are very huge deviations from each of the chains. As you can see here, the first steps of each chain were also recorded without burning samples. And as you can see here, these are the starting values of each of the chains. So this is basically useless. The autocorrelations, as we saw earlier, are with significant differences between chains, and also one of them not proximate to 0. The shrink factor is going, they are all above 1.1, and the density are pretty different between each chain, especially the light blue chain, and also the 95 confidence intervals credibility intervals, sorry, can be very different, and the standard error can be also higher. Okay, what we can do if we have a problematic MCMC going on. First of all, check for bugs. They can be just as simple as finding some bug in the script that you are getting into to just get a solution to this problem. Another common solution to have is to increase the iterations, but it's important to don't be excessive and not be like 13 hours of an MCMC, because you are wasting time and resources unless you can afford it. In addition, you can also increase burn-in iteration just to be sure they are not mixing in with the inference. Other potential solutions to specify starting values. This is useful if there are big discrepancies between the literature and data. It's just to make it easier for the MCMC to find the best zone to draw the posterior. Other potential solution is to increase the number of chains, normally a maximum of 5. This is very rarely seen, because the computation power just scales up. And if you imagine that you have a 9-hour MCMC going on with 3 chains, so it's basically 3 hours per chain, more or less. If you increase that to 4, you will end up with a 12-hour MCMC going on. So it's not very advisable, unless you don't have any alternative. Okay, other thing to try is to change the prior. For example, the prior is weak or not very well justified from the literature. Maybe it's too broad, or maybe it's included values that are out of the metric of the parameter or having unrealistic values. Therefore, you can increase the informativity if you can afford it from a theoretical point of view, because it will restrict the MCMC for dancing around. And also, you can change the distribution model. For example, you can shift from a normal distribution to a Cosette's T or student's T distribution and see if this improves the situation. Another thing to try, for example, would be to crop a distribution, for example, a normal distribution, because you are expecting values that are between -1 and 1, and therefore you can make a truncated normal as the prior, and then make it a little easier for the MCMC to not get out of these values. Another common technique to find, but is more expensive, is increase the sample size, because maybe the data is too weak to identify this model. And finally, you can change the metric of the variables if admissible to make it easier. For example, if you are working with country populations and you are working with predicted values that have decimals, you just can round them. Or maybe you can shift the metric to a log transformation or something like that, okay? So, as a summary, we need the MCMC to have representative values. To assess that, we have the trace plots and the potential scale reduction factor, and also plot the density or histograms to have a clear form and without many differences between each chain. And also, then we need these values to be precise. Therefore, we need low autocorrelations and without differences between chains, an effective sample size above 10,000, and also a Monte Carlo standard error with a theoretical sense. So now, how we can do that with software? So one of the best alternatives out there is JAX. It's called Just Another Gibbs Sampler. This is the successor of one of the biggest samplers in Windows that were available back then. It was called Box or WinBox. And also JAX is better than Box. And it has an interface in R, for example, RJAX or RoundJAX. And also JASP has an interface in JAX. So yeah, it's kind of pretty standard right now. However, JAX can be slow, very precise but very slow. There's a really nice alternative that is called STAN. STAN has also interfaces in R that are called BRMS and RSTAN. That STAN can be more efficient regarding space and time, and also just as precise as JAX in many occasions, because it has pre-compiled distributions in it, and therefore for many advanced techniques in Bayesian inference, STAN is the preferred choice. There are also other options, for example in MATLAB or also Python interfaces. So yeah, the main players in this market are going to be STAN or JAX.